Right, this video is a quick little video introducing you to the maths content that you're expected to know for the exam. If you look at the OCR website, the specification on their website, sorry, it's a big long PDF. You should be able to get it on our Moodle page as well. It gives you the whole lowdown on what is expected of you in the course. Page 87 onwards gives you a list of all the mathematical expressions and formula you need to know. So it's a really good idea just to go through this as a checklist, certainly when it comes to revision. Just scan through this as well, just to make sure you're familiar with everything in it. Now, it's broken up into 7 strands, different types of applied maths. Basically, it might be electrical theory, it might be mechanical, etc, etc. But there are some useful things that you can check that you know or not. For example, cosine rule. I've seen an exam where this isn't supplied. You're expected to know this one, as with this one. So for those of you that haven't covered it before, it's a formula that you can calculate any of the lengths of the faces of the edges of a triangle given one angle. Let's say you've got one angle and 2 of the 3 sides of a triangle length, and you're expected to know the final side. And that works for any triangle, it's not just a right angle triangle. We'll cover that in more detail, but yeah, that kind of thing is important just to try and memorize. Now there are other things, for example, these velocity formula here. I've seen a question where you are given this formula, but you are expected to know what u is, initial velocity, v, final velocity. S, what's that? Displacement. What's displacement? It's a vector distance. So in other words, a distance given with a given direction, and so on. So yeah, it's important to know quite a lot of these formula as well. It's important to understand the terms. So, for example, S being displacement, knowing what that means. All too often, you might be given a simple formula like Young's modulus equals stress over strain, but you're not told what stress is. You should be by now expected to know that. What is stress? It's a force per unit area. It's a bit like a pressure. It's a force subjected on a material given how thick it is. Obviously, a little tiny wire is going to be a lot more stress, under a lot more stress if it's subjected to 100 newtons of force than a massive great steel girder. So the unit area is quite an important factor there. Now, my first top tip when doing an exam, you might well forget a formula, that's fine. It's really useful that quite often you'll see in an exam, let's find an example here, should have one to hand ready, but you'll find that the answer they're expecting from you is quite often given with its units. So for example, in fact, I think there is a stress question here, further down. There you go. Newtons per meter squared. So when it's asking for a question here, it tells you the units. Now that could be really useful because you should be able to work out newtons, that's a force. -2 here means per meter squared. So it's the same as n over m2. Okay, so that should be enough to make you realise that to get this stress you need to work out a force and an area and divide the two. So it's a really useful thing to look at the units that they're asking for. Now, as well as that, be careful as well. So all too often they like to challenge you with making sure you've converted the units properly. You'll notice in this case, our area, our cross-sectional area, which you're asked for here, I confess when I tried this question I failed to notice they're asking for it in meters squared rather than millimeters squared. Now it's important here, and a lot of students get this wrong, to understand the difference between millimeters cubed and millimeters, for example, or meters squared and centimeters or million meters squared. What do I mean by that? Well, let's take, for example, and I'm now going to demonstrate my terrible use of a graphics tablet. It's a lot harder to do this than a whiteboard. But let's say you've got a sugar cube here, a centimeter cubed. So each length, see what I mean about the drawing? It's terrible. That's a centimeter. They're all a centimeter width, depth, and height. Now, a meter of sugar cubes in a line, 100 of them, all agreed, yeah? So if there's 100 centimeters in a meter, we've got 100 sugar cubes in a line of a meter. Now, assuming there's no gap in between them all. What if you were to have a tray, which is a meter squared? Again, excuse the drawing, but let's say there's that sugar cube on the corner of it. So we've got 100 sugar cubes in a meter line like that, but this tray is a meter by a meter. So you've got 100 rows of 100 sugar cubes. You've got 10,000 centimeters cubed there. Sorry, centimeters squared. Okay, on that meter squared tray. Now, that tray goes into a meter cubed box, so 100 of those centimeter tall, assuming that tray is 0 thickness, and you stack these sugar cubes into a meter cubed. So we've got 10,000 on that tray, another 100 trays to make a meter in depth. 10,000 times 100 is 1,000,000 centimeters cubed in a meter cubed. So bear that in mind. Now back to this question here. We've got millimeters squared and millimeters. So how many millimeters are in a meter? Well, there's 100 centimeters in a meter, so there's going to be 1,000 millimeters in a meter. So when you're talking about millimeters squared, how many millimeters squared in a meter squared? It's basically 1,000 times 1,000. So we've got 1,000,000 millimeters squared in a meter squared. So be careful here when it's asking in meters squared. Now, this isn't necessarily a great example, but quite often in exam questions, they're giving you everyday scenarios. For example, okay, a 1.6 millimeter diameter cable. You can visualize what kind of size that is. Pretty tiny little wire. Okay. When you're working out an area in meters squared, ask yourself, does that sound like a realistic amount? Now, like I said, this isn't a great example because it's not very easy to visualize a wire area in meters squared. But let's say there's another question, past paper you'll probably come across, where you're asked to look at the volume of polystyrene in a bike helmet in centimeters cubed, I seem to remember. Now, again, you're going to convert the units. So when you get the answer, it's a good idea just to look at that answer and visualize how many cc's, centimeters cubed, there are of polystyrene. And is that the kind of amount you'd expect a bike helmet to be made out of? If you get the units wrong whilst you're converting them, chances are you'll be 10,000 out, or if you divide it instead of multiply it, you'll probably come up with an answer for a bike helmet being made out of 0.00007 centimeters cubed of polystyrene. You can look at that and go, that's wrong. It's a good idea just to be on top of that. Make sure what you're doing is correct. So yeah, watch out for units. Look out for given formula, but also answers units as well, like that, because that can really help in knowing which formula to use. So in successive videos, we'll just go through all of this in a little bit more detail. A few other, basically, I'm just going to cover the overview as well. Standard form, that's a really useful one to know about. Quite a few students come into design engineering without an understanding of it. So what do we mean by standard form? significant figures and decimal places as well. They're relevant to this as well. So, for example, we've got this number here. Oops. Let's say 12345.6789. Okay, if they ask you to give the number to 2 decimal places, then that would be 1, 2, 3, 4, 5, and then the 2 decimal places here. And the last one, we look at the next decimal and decide whether we need to round that up or keep it the same. In this case, it's over 5, so this is going to be rounded up to 68. Okay, get that right, because sometimes you will be penalised if you're asked to do it to 2 decimal places and you just write 6, 7. You'll probably lose a mark there. So just be careful. You make sure you get it to the right amount of decimal places and you round up or you round down. Now, what's significant figures? Instead of looking at the fraction after the whole number, we're looking at the whole thing. So in other words, if we're asked to write this to 3 significant figures, let's say this is a sensor reading on a I don't know, a thermistor, and it's got a big long number of fractions after that. Once we've done our calculation, they're all relevant, especially when it comes to the accuracy we're dealing with. So really, we're only looking at that kind of magnitude of value. This is all relevant. So again, these numbers here, we just get rid of them, but we need to obviously keep the unit. So in other words, we know this is in the order of 10,000. So that would be 1, 2, 3, 3 significant figures, and then 0, 0. So that would be the answer to 3 significant figures. Now, quite often you're only going to see significant figures when they're written in standard form. What is standard form? Well, this number, basically, we start off with the first bit of it, which is basically a number from 0 to 10. So it's just basically a unit value up to 10. So in this case, it would be 1.23. And then to convert this number to this number, we say times 10 to the power of however many times this decimal point has been shifted. So in other words, this is 1, 2, 3, 4. So 10 to the power of 4. That is this number to 3 significant figures. Now, quite often it's a lot easier to play around with numbers. So let's say we're going to times this number by 2 million. Oops. Okay, sorry, this pen seems to be... I'm blaming the tools. So what is 2 million in standard form? Well, that's 2 times 10 to the 6. Okay, so it's got 6 noughts after it. So without needing a calculator or getting bogged down with how many times you're counting off noughts and stuff like that, if you're going to be adding, multiplying these 2 numbers together, it's going to just be these 2 multiplied, so that would be 2.46, and these powers are added. So 4 plus 6 is 10. Okay, and that would be a very big number in terms of how many noughts it would be. It would be basically that decimal place has been shifted to the right 10 times as well. So it would have 8 noughts after that 4, 6. So yeah, standard form is an important thing to play around with. If you're going to be multiplying 2 big numbers like that, then obviously the powers get added. If you're going to divide them, then you would subtract this one from that one. If it goes into a negative number, you're obviously doing a very tiny fraction, getting a lot less than I don't know, 1s or 2s or anything like that. Okay, the other thing as design engineers you need to know about is millis, megas, gigas, nanos, picos, and stuff like that. So what's what? well, let's start with the easy one, milli. So millimeters. 1 millimeter is 1,000th of a meter. Like that. Okay, or 1 times 10 to the minus 3. Okay, I'm going to just go new again. So let's do a little table. So there's 1, and then milli is to the minus 3, and then what's the other way around? Well, kilo is 10 to the 3. Mega, 10 to the 6. Megabytes is 1,000,000 bytes. Giga, 10 to the 9, so it's 1,000 million, billion in UK term. And then tera is 10 to the 12, that's 1,000 gigas. The other way around, micro is to the minus 6, and nano is to the minus 9. Okay, so they are useful things as well. You're expected to know these as engineers, so if you don't know it, just copy it out, figure it out off by heart. Find some kind of mnemonic, it's quite a useful way of learning that kind of thing as well. The other thing to bear in mind as well are greater thans, less thans, equal to. So what? Just getting the right way round. So A, that way round. B, what does that mean? A is greater than B, because the wider bit of this bracket is on the A side. A is greater than or equal to B. A is less than B, etc., etc. So just keep an eye out on which side the small bit of it is and which side the big is. So A is smaller than B there. That's easy. When you know it, it's easy to figure it out like that. Okay, so just remember, quite often they will be giving you the formula, but you will still need to know what the letters mean in the case of one of these velocity equations. Yeah, you'll be expected to know how to use it, even if you're given it. And then in other examples, you might, like the this one here, the cosine rule, you're asked to remember this formula. So yeah, it's important. It's a really good idea just to go through this checklist basically over and over again, especially just before your exam, whenever you do it. So yeah, let's go on to the next video and we will just cover this in slightly more detail. Okay, thank you very much.